Okay, picture this. You're running something critical, maybe a hospital, a big factory, even a data center, and suddenly the power just flickers. Almost nothing, right? A voltage sag. It might only last milliseconds, but boom, equipment malfunctions, production stops. We're talking potentially millions in losses. It's this kind of hidden threat in our super connected world.
Oh yeah, it's a massive issue. And we actually have tech to fix it, things like STATCOMs. They're a type of fax-dias device, flexible AC transmission system. They smooth out those sags. But the tricky part, figuring out the best place to put them in this enormous power grid, historically that's been, well, just incredibly computationally heavy.
Right, the sheer scale of the grid itself was the bottleneck. Just too much data for the old ways. So our mission in this deep dive is to unpack this really intelligent new approach, one that drastically cuts down that computational work, making sure these vital statcoms go exactly where they're needed most to make the grid more resilient.
Exactly. Voltage sags, they're a major power quality headache.
Right.
And they hit the bottom line hard. Statcoms help because they improve what's called the SAR-Phi index system, average RMS variation frequency index. Think of SAR-Phi like a grade for grid stability. Lower number, fewer sags, better power.
Okay, so a lower SAR-Phi is what you want.
Right. But StatComs aren't cheap to install or maintain, so you absolutely have to place them optimally. You need efficiency.
Okay, so if the goal is smart placement without getting buried in calculations, how does this new method even start? What's the first clever step?
Well, the really groundbreaking part is how it observes the grid. It doesn't try to watch everywhere. Instead, it intelligently picks out the minimum number of monitoring buses needed. So, for instance, on a standard test system, the IE14 bus, they found just 3 were enough buses, 11, 13, and 14.
Only 3 for the whole system.
Yep, and it's not random. They focus the monitoring based on the single phase to ground fault. That's a really common disruptive kind of short circuit.
Ah, so they target the worst case common scenario?
Exactly. Ensures good coverage for big problems, but with way less data. That's the first big saving.
Okay, so identify those key representative points first. Smart. What's the next layer? How do they cut down the analysis even more?
Then they identify what they call areas of vulnerability, AOVs, around each of those monitoring buses.
Right.
So instead of simulating faults across the whole network, which takes forever,
Right.
they only run detailed studies inside these specific high-risk zones.
Ah, like a focused investigation.
Precisely. It's like using a smart searchlight, pointing it right where problems are most likely instead of just flooding the whole area. Much more efficient. Targeted.
That makes a lot of sense for the areas you are monitoring. But what about everywhere else? How do you get the full picture without, actually looking everywhere? Seems like a bit of a jump.
Yeah, that's where the data science really comes in. It's pretty neat. To understand those unmonitored spots, they first build this massive database. They use Monte Carlo simulations, basically running thousands upon thousands of random scenarios. It's like simulating, say, 4,000 years of grid behavior to capture a realistic range of possible voltage sags.
4,000 years. Okay, so you get a really robust baseline of what could happen.
Exactly. A very realistic picture.
And then how do you link that back? If you see something at bus 11, how do you know what's happening at, say, bus 5?
Good question. They use something called Pearson correlation. It basically measures how strongly voltage sag patterns at different buses are related.
Okay, so if bus A sags, bus B often sags too.
Yeah.
That kind of thing.
Right. It maps out those connections. And then they bring in the Bayesian theorem. Think of it like weather forecasting. If you know the readings at a few key weather stations, and you understand how weather patterns link across the region.
You can make a pretty good guess about the weather in between those stations.
Exactly. Bayesian theorem lets you use the data from the few monitored buses, plus those correlations you found, to make really accurate estimates for all the unmonitored buses. It's smart inference.
That is clever. Using knowns and relationships to figure out the unknowns.
Okay, so now you've got this estimated picture for the whole network. How do you finally pick the absolute best spots for the StatComs?
For that final step, they use a genetic algorithm, or GA. It's a type of meta-heuristic search method, very powerful. It basically mimics evolution. It tries out many possible placement solutions, lets them compete, and evolves towards the best one over generations.
So it avoids getting stuck on just a good enough solution. It really pushes for the optimal.
Precisely. Finds the most effective locations very efficiently.
Wow, okay, so tying it all together, what happened when they tested this on that IE14 bus system you mentioned? Did it work in practice?
It worked really well. The method pinpointed pinpointed buses 10, 13, and 14 as the optimal spots for STATCOMs, and installing them there resulted in a total SARFA index of just 45 for the entire network. 45. And that's considered a good result.
Oh, absolutely. Especially achieving that across the whole network using this targeted data light approach. It proves you can get that comprehensive network view, make smart decisions without the insane computational cost. Think of the savings, the reliability boost for industries.
So this deep dive really showed how focusing smartly, minimum monitoring vulnerable areas, and then using clever data science can completely streamline this super complex job of keeping our power quality high.
Exactly that. You get the big picture insights, but in a way that's actually practical, economically, and computationally.
It's amazing, isn't it? These kinds of unseen engineering feats happening behind the scenes makes you think how innovations like this are constantly working, quietly making everything from your Netflix stream to hospital equipment just more reliable day in, day out. It's that invisible backbone keeping things running smoothly.